Right. Today, I'm going to talk about a testing technique for multi-core OCaml programs using a tool that we developed called Paraphos. This is joint work with my students, Sumit and Adarsh. So multi-core OCaml is an extension of the OCaml programming language that adds native support for concurrency and parallelism to OCaml. By concurrency, I define overlap execution of tasks in time, and parallelism is defined as simultaneous execution of multiple tasks in time. And in keeping with the separation, multi-core OCaml provides distinct mechanisms for expressing concurrency and parallelism. For concurrency, multi-core OCaml provides what are known as effect handlers, and for parallelism, it provides a mechanism called domains. The focus of this talk is going to be testing parallel programs written using domains using the concurrent programming mechanism in multi-core OCaml. So let's take this parallel program written using multi-core OCaml as an example. So in this program, we have a function test that takes an input I, which is an integer, and it creates two atomic variables x and y, where y is initialized to 0 and x is initialized to the input value I, and it spawns a new domain. And the new domain reads the atomic variable, and if the value is 10, then sets the atomic variable y to 2. In parallel, the parent domain sets x to 0 and y to 1, and then waits for the newly spawned domain to terminate. And after that, it asserts that the value of y is not equal to 2. Now the question is, can this assertion fail? Yes, it can. It fails for a particular combination of input and thread scheduling. In particular, if the input value to this function is 10, and the newly spawned domain happens to read the value of x before it is written by the parent domain, but the write to y in the parent domain happens before the write to y in the newly spawned domain, then the final value of y will be 2, and this will falsify this assertion, right? And the point to notice here is that these sort of bugs are what I call logic bugs. These are much more than just detecting data races, right? And in particular, there are no data races in this program, right? So even if you were to use a language like Rust, which avoids data races by construction, these sort of bugs may still manifest. So our goal with this work is to build a tool that is an effective and pragmatic tool for testing these sort of programs applicable for the working OCaml programmer, right? Who has a limited time budget and they want to sort of catch these sort of bugs. Okay, so that's the goal for this work. So what are some of the existing solutions? You can stress test your program by running the program over and over again in the hope that the assertion is triggered. Or you can be a little bit more intelligent, where you generate random inputs for the program, but also perturb the OS scheduler somehow in order to trigger the bugs. Unfortunately, these sort of testing techniques are not very effective because of the large input and the schedule space of typical programs. You can do model checking using model checkers such as Spin and TLC. These have very strong guarantees, but are not practical if one has a limited time budget. And there is often the case that there is air gap between the models that you actually model check and the actual source code that you want to execute. Finally, you can try formal verification, but this requires expert knowledge and lots of time and effort. And formally verifying concurrent programs is also hard even for experts. So our goal is to look for pragmatic testing techniques and to build on top. Right? So let's ignore concurrency for the moment and only focus on input non-determinism. In this case, there are a few techniques that we can build upon. The first is property-based testing, where the idea is that you sort of give a property that you need to test And then you also write a generator in order to generate random inputs to test a function. This technique was first introduced by QuickCheck for Haskell, which has been very effective and has been cloned in many, many languages. The other technique is fuzzing. And the idea here is to generate random inputs in order to crash a program. And the prototypical example here is American Fuzzy Lock, AFL, which is an extremely effective fuzzer. And it is also a gray box fuzzer. What does that mean? A gray box fuzzing compiles the program under test with instrumentation that sort of emits some information about the paths that are taken by the program back to AFL. This coverage information is very useful because AFL can see what paths the program has taken and try to mutate the inputs in order to see whether the program goes into a different path, and thereby maximizing coverage and detecting bugs. Right? And there is this tool called Crowbar for OCaml, which combines fuzzing with QuickCheck to do what is known as coverage guided property fuzzing. This has been very successful and has been applied to many OPAM packages and has found a number of bugs, right? So building upon these techniques, what is Parafuzz? Parafuzz is a combination of a Crowbar, which itself is a combination of gray box fuzzing plus property-based testing, applied to parallel programs, right? And what is our particular challenge here? Our challenge is to control parallel thread scheduling. So when you run a typical parallel program, the operating system controls the thread scheduling. But in order to trigger these hard to find the concurrency bugs, you need to force a particular buggy schedule. So you need somehow to control the parallel thread scheduling, right? How do we do that? The way we do that is through effect handlers. So we mock the parallelism API using effect handlers. So what are effect handlers? Effect handlers are this modular and composable basis of non-local control flow mechanisms, including exceptions, async await, lightweight threads, coroutines, etc. From an operational point of view, effect handlers provide a structured programming mechanism over delimited continuations. So we use effect handlers in order to simulate a parallel thread scheduler over the domain API. And what we end up getting in return is that we don't use the OS thread scheduler anymore. Operating system threads are mapped onto user level threads, and the operating system threads scheduler is actually now translated to a user level thread scheduler, where we retain control over the scheduling decisions, right? And now what we do is we actually fuzz the scheduler. And how do we do it? At every synchronization point, a synchronization point is a point where if you context switch, you lead to some non-determinism. So at every such synchronization point, we actually force a thread yield. And what do we yield to? Here is where AFL comes in. So we actually leave the decision of the next thread to run from the ready queue for AFL. So AFL gets to sort of pick the next thread to run, and the path information sort of is fed back into AFL, and AFL can see whether it has the program has sort of gone into an interesting path which it has not seen before. So what are synchronization points? These are what you would expect, right? The points where you spawn and join domains, where you read and write and compare and swap atomic variables, lock and unlock mutexes, wait, notify, and broadcast on condition variables. So the whole system looks like this. So you would take the program that you want to test, you will compile it with a special compiler that adds instrumentation, and it is run as a daemon with AFL. And AFL sort of supplies the input to this program, but also the thread execution order. And the instrumented program emits the execution path information back to AFL so that it can generate more interesting inputs in order to force the program to go towards the buggy path. So there are several advantages to using Parafuzz. Parafuzz is a drop-in replacement for multi-core OCaml. if you want to test the programs using Parafus, you just need to install a separate compiler switch, add your assertion, write a generator, and off you go, right? And there are no false positives in the system. If a bug is found, it is a true bug. And when a bug is found, we also get a trace. That is a deterministic trace, which allows us to replay the executions and debug the program. So how effective is this technique? So we take the same example as that we've seen earlier. We are comparing 3 testing techniques here: Parafus, random testing, and stress testing. And the main takeaway is that Parafus is the only one that was able to find the bug. Random and stress testing were not able to find the bug in an hour, right? We terminated the program in an hour, and Parafus was able to find the bug within 10 minutes. Random and stress testing were able to do many more executions, but still were not able to find the bug because it was not heading towards interesting schedule and input combination. Right? That's the reason why Parafus was able to find the bug in this case. We also evaluated the technique on a number of known bugs that were taken from other papers. These included bugs that were due to racy conditions as well as deadlocks. We were interested in 2 metrics. The first is effectiveness. So what fraction of the runs does the tool actually find the bug? And the second is efficiency. What is the mean time to failure? Right. So we ran the program. We ran each of these test cases for 30 executions for each tool, and we report here the fraction of executions that found the bug. And what you see in this table is that Parafus was able to find the bug in every execution except one in the CL circular list example. Stress testing was not able to find any of the bugs, right? Random testing was able to find the bugs in every execution in this one case, which is domain slip, and one other execution in this BI example. So Parafus turns out to be much more effective than stress and random testing. And in terms of efficiency, you can see that these numbers reported here are in minutes. So Parafus was able to find, seconds. Parafus was able to find bugs within a reasonable amount of time, right? So less than around 15 minutes to half an hour, right? And even in the case where the random testing found a bug, Parafus was able to get to the bug 5 times faster, right? So Parafus is both efficient and effective. So one particular future extension that we are considering is encompassing programs that have data races as well. So currently Parafus assumes that programs are data race free, and data race free programs in multi-core OCaml have sequentially consistent semantics. This is what allows us to only insert yield points at the synchronization points, right? And still have coverage because our program has SC semantics. But what happens to programs that have data races? So our PLDI 2018 paper shows that for OCaml, we have a very simple operational model that describes the behavior of racy programs compared to, say, the complex operational models that you have in, say, C++ or Java. In particular, in multi-core OCaml, a racy read may return one of a subset of writes that have been performed to a particular atomic location, right? So using this simple model, we can actually extend Parafus to test the racy programs as well. And the idea here is to use AFL to pick the value that a read should return, and also force a yield at every non-atomic read and write, right? And the challenge here is the latter, right? Can we actually make it fast enough for pragmatic use is the question. This is yet to be seen. In order to summarize, Parafus is a property-based fuzzing tool for parallel OCaml programs. It is easy to use. There is a drop-in replacement for multi-core OCaml programs with a separate switch. And the results show that the technique is effective and efficient at detecting concurrency bugs. Thank you. I'll stop here.